Our potentiometer works by displaying in the serial monitor as a value between 0 and 1023. This is because of the Arduino's inbuilt 10-bit resolution ADC, or analog to digital conversion, which means that it can convert any incoming voltage into a value anywhere between the range of 2 to the power of 10. The value is then printed to the serial monitor and is thus able to be viewed by the user. Our LED's brightness is adjustable by mapping the potentiometer value directly to a PWM signal, which is then sent to the LED and adjusts its brightness by adjusting the frequency of the power it receives. The timer for our LED uses millis as their non-blocking operations. This means that the code can be run at the same time as other code without interrupting it. Our LEDs are controlled by assigning values for a blink color function. This includes an interval, a duration, and the color of the LED. This is achieved by using modulo arithmetic, which divides the current time by the interval and provides the remainder, effectively determining how far into the current blink period we are, thus controlling the LED's state, which is either on or off. Here is a demonstration of the code in our flowchart and in practice. We determine the frequency of the blinking by dividing the amount of blinks by the time. Once loop flashing is completed, our code waits 5 seconds before turning the red light off and the green light on, and returning to the beginning of the loop. As shown here in our flowchart, our code then performs a check. If the lock button has been pressed, it waits 3 seconds on the green light, begins to blink, checks that the amount of blinks has elapsed in 6 seconds, initializes the SSD countdown. Our SSD functions by using an integer array, which stores the values of all numbers we need to display. And functions by storing a value, either 1 for on or 0 for off, for each segment of the 7-segment display in a row. In our program, we store 10 values, 1 for each number between 0 and 9. This is shown in our integer array, and the segment of code, which updates the SSD every second, displays the current value, decreases the countdown, and then turns it off at the end. Here is a demonstration of the code in our flowchart and in practice. Our code then turns a solid yellow LED on for 5 seconds, then blinks the yellow LED for 4 seconds, before returning to the beginning of the loop. Our status is reported every second through the use of millis, which are a constant value. They are reported under the function serial print time. Every 1000 milliseconds in serial print time, the state, inputs, and outputs are printed to the serial monitor without delaying the rest of the code. Our program uses more than 2 custom functions with inputs and outputs. For instance, we use output for our LEDs as our output devices and input pull-up for our buttons, as the use of built-in pull-up resistors reduces complexity and increases stability. Here you can see our wiring diagram, which shows our use of internal pull-up resistors, as well as the wiring for our 7-segment display, potentiometer, and LED. We determine the value of the resistors needed based on the following calculations. The coding of our program, we encountered multiple problems. The most memorable was finally understanding how to wire the potentiometer. Before solving this problem, we could not understand why our serial output was only printing a value of 0, which we later determined to be due to incorrect wiring of the wiper, which did not send any signal to the board. We diagnosed this issue by realizing that a continual 0 value meant the potentiometer could not be correctly connected and thus made a hardware issue probable. This was then confirmed and rectified. We amended this, and this allowed our LED to output light and let our program function. Coding programs and technical systems is very different when working alone and in group settings. This is largely due to the way in which individuals approach problems and the value of discussion in coding. Since coding doesn't necessarily have a set solution for most problems, it's easy to find solutions with a group mate as you're able to brainstorm and bounce ideas off one another. Adversely, it is harder to work on programs alone as you're limited by your own knowledge and understanding, but also by your own thought processes and the way that you deal with problems. For instance, I believe that my strength lies in practical knowledge, which may help in the design of the breadboard, and my weaknesses lie in coding. This means that my group mate and I can each work to our strengths and produce a more refined and overall better program and system as compared to working alone. These differences also affect the way in which the task is approached, leading to my focusing on the script, visuals and editing and design, and my group mates' focus on the coding, although we helped each other with our tasks. The improvements between A1 and A2 are plentiful. Firstly, the implementation of millis as compared to delay has reduced the length of our code and improved its legibility. Also, the fact that millis are non-blocking functions means that we can easily integrate tasks that require inputs at varying intervals, such as our LEDs, and allows the function to iterate much faster by preventing blocking, which is when code stops until the timer on the delay function is finished before moving on to the next line. A further improvement on A1 is the introduction of analog signals, which unlike digital signals can provide a range of values. This has allowed us to add brightening and dimming functionality to our system, which improve the quality of life for the end user. Another major improvement made in the latest iteration of our design is the improved use of variables. The importance of the use of variables not only lies in their ability to store data, but in the way in which their introduction reduces unnecessary clutter in our code, which improves legibility and makes debugging faster and easier.